Now that we know that rational tangles can be built out of t's and r's, the twists and the rotations, and we know enough about the algebra of how twists and rotations interact to be able to understand a presentation for the rational tangle group, we want to take that a step further and see if we can use more familiar and friendly algebraic objects to stand in for rational tangles and mimic their behavior. We're going to do that in a two-step process. First, by representing the t and r generators of the rational tangle groups as functions, which feels like a step backwards because functions can be very complicated. But the good thing about functions is that they're very versatile. And so we'll be able to craft a couple of functions that interact with one another just like the twist and rotation in the rational tangle group do. And then, the coolest part of all, is we're going to prove that we don't have to use entire functions to capture that behavior. It turns out we can use a single rational number called the fraction of a rational tangle to completely represent the entire structure of that tangle. This is the real shock, that we can have a complete invariant for rational tangles that consists of a single rational number. In these two videos, we're going to walk the path that lets us discover how that's done. So first and foremost, the question is, can we find a group of functions that can mimic the behavior of the elements in the rational tangle group? Tangle words. Let's unpack that question just a little bit. First of all, when I say functions, I really do mean functions in the sense of high school algebra. Functions that we're going to call little t and little r, that we're going to hope their interactions can capture the behavior in algebra of the rational tangle word generators, capital T and capital R, the twist and the rotation. And for us today, these are going to be functions which take an input, have a domain of rational numbers, and which give us an output, have a codomain, also of rational numbers. So we feed these functions a rational number, they spit out a rational number in return. So those are the kinds of functions we're going to be working with. Now the word group in this question is doing a lot of heavy lifting, because we have to specify in what sense are we going to think about these functions forming a group. What is the operation of that group going to be? So if I think of functions which take rational numbers and produce rational numbers, an operation we can use to turn that set of functions into a group is the operation of composition of functions, the operation where I feed the output of one function into the input of the next. So if you give me two functions f and g, then in this group, f multiplied by g is going to mean f of g of x, the function I get by composing g of x followed by f of x. And if my functions are invertible, that means that we have another function we can compose them with to turn the composition into the identity function. Then we can show that this forms a group under the operation of composition. So the operation we're going to think about in our group of functions is composition of functions. And the identity element is therefore a function which, when I compose anything with it, doesn't change that function that I compose it with. And when we say mimic the behavior, what we mean here is the same thing that we meant when we were talking about braids, which is we just want to know that these things we're using to represent the elements also interact with one another according to the same relations that were present in our rational tangle group. And there were two relations in the rational tangle group. The first is that the rotation was an element of order 2. That was a surprise with rational tangles because nominally our rotation element was just a 90-degree clockwise rotation. And so we would think that it would take us 4 rotations to get us back to the identity for rational tangles. But in fact, we found out that doing it just twice, a 180-degree rotation of a rational tangle, actually gives me the same tangle as we started with. So the rotation was an element of order 2, so r satisfied the relation r squared equals the identity. Likewise, when we were hunting for an inverse for the twist operation t, we found out that doing t followed by r 3 times in succession, twist, rotate, twist, rotate, twist, rotate, also gives us the identity operation on any rational tangle. So r is an element of order 2. T composed with r, twist then rotate, is together an element of order 3. If we can find functions that also capture that same behavior, then we might be in business. So I want a little r function. If it's going to represent the rotation, we need it to, when I compose it with itself twice, we need to be able to get the identity function. And likewise for t followed by r. When I compose t followed by r with itself 3 times in succession, I need to get the identity. One thing to be careful about here is I'm saying t followed by r. We read these rational tangle words from left to right. So tr means twist and then rotate. But in the land of functions, If I do a t function followed by an r function, then we're working that function notation from the inside out according to the order of operations, right? So tr as a rational tangle word is going to be represented by the function which does t first and then does r afterwards, right? And so it's going to look like t of x with r of x wrapped around it. So tr composed with itself 3 times is going to look like t followed by r, followed by t, followed by r, going from the inside to the out, right? So the way that we write function notation in composition land sort of looks backwards from the way that we're writing rational tangle words to be read from left to right. That's just something to keep in mind as we go through this process. And the role that the identity function is going to play here is we need a function which, when we compose any function f with my identity function, we get f back again. And the identity function is played by this function e of x equals x. It's a function which does nothing to its input. Whatever input you give it, it just gives you that same thing back as output, right? So it's just like a pass-through, right? We throw the x down the top of this function, and then the same x falls out the bottom as output, right? We can show very quickly that that function, e of x equals x, operates as the identity element of the group of functions whose operation is composition. So that's going to be my identity function. That's going to be the function that I want to get when I compose r with itself twice and when I compose tr with itself 3 times. The problem is, again, that the land of functions is a vast, undiscovered country. Right? So it makes sense for us to kind of fence off an area of functions that we want to try and explore to meet these needs. And the class of functions we're going to work with are a very versatile class of functions called the Mobius transformations. The Mobius transformations are functions which are built out of a quotient of 2 linear functions, f of x equals ax plus b in the numerator, divided by cx plus d in the denominator, where a, b, c, and d are all going to be taken to be rational numbers, so that my function can take rational input and produce, for sure, rational output. So any function we can write that has a formula like this is called a Mobius transformation. And what's great about Mobius transformations, what makes them so friendly to work with, is that when I compose 2 Mobius transformations together, I do f of g of x, I get another Mobius transformation, for sure. So the Mobius transformations are going to form a subgroup, if we can also guarantee that they're invertible, which you'll figure out in this activity how to do. But then also, the nature that that composition takes is very predictable. In fact, it's a reflection of a different kind of algebra that we know from elsewhere. If I take the coefficients of this Mobius transformation out and I write them as a 2 by 2 matrix, and I have another Mobius transformation, g of x equals a prime x plus b prime over c prime x plus d prime, and I write those coefficients out as a 2 by 2 matrix, then if I multiply these 2 matrices together using matrix multiplication, row by column, right, I'm going to get this nasty looking 2 by 2 matrix. But the coefficients of that 2 by 2 matrix are exactly the coefficients of the Mobius transformation that we get by composing f of g of x. F of g of x has those coefficients that make it up. So Mobius transformations compose with one another in exactly the same fashion as their corresponding matrices multiply with one another. Composition of functions for Mobius transformations is exactly parallel to matrix multiplication of 2 by 2 matrices. So that makes this group of functions really nice and easy to work with. We can do a lot of algebra with them without having to worry about function composition, because we can trade out composition for matrix multiplication, which we have a lot more tools to work with. So what can we do? We can look for a Mobius transformation which has the property that when I compose it with itself, it gives me the identity function, e of x. Right? And if we do that with Mobius transformations, that's the same thing as looking for a 2 by 2 matrix, which when I multiply that 2 by 2 matrix with itself, gives me the identity matrix. And that seems like a fairly tractable search. Right? It's something that we can do just by sort of playing around with the coefficients in 2 by 2 matrices until we get it just right. What we're finding there are functions that are called the functional square root of the identity function. When I compose them with themselves, the result is the identity function. Similarly for the generator tr. Any Mobius transformation which I can find which has the property that when I compose it with itself 3 times is going to give me the identity matrix. In other words, a matrix, a 2 by 2 matrix, which when I raise it to the 3rd power, multiply it by itself 3 times, I get the identity matrix. Such a Mobius transformation would be a good candidate to represent tr. Right? So what we're doing is we're just looking for a Mobius transformation that has order 2 and a Mobius transformation that has order 3. If I can find one of each of those, then the latter is a good candidate to represent my rotation, and the former, and the latter is a good candidate to represent t followed by r. In other words, r of t of x. Right? And if I know those two things, then I should be able to put those two pieces of information together to determine what is really representing t, my twist. So at the end of this activity, what you'll have are some candidates. Right? Some Mobius transformations that you think can represent r, and some Mobius transformations that you think can represent tr, and from that you can find some Mobius transformations that we think can represent t. Those are going to be the candidates we'll carry forward to try and figure out how to capture the algebra of rational tangles using an algebra of functions instead.